702 and Cape Talk.
The Naked Scientist.
Morning, Chris.
Good morning, Eusebius. How are you?
I'm extremely well. I hope you are also. I think our science story this week, what are we touching on? The Nobel Prizes.
Well, it's a pretty important week for science, isn't it? Because, yes, the prizes that recognise the pinnacle of human scientific endeavour have been announced this week. The prizes for chemistry, physics and medicinal physiology. So I thought it was worth giving a nod to who's won what, because it's also an interesting year for a range of reasons. The physics prize, there were three winners. There's a guy from the US, he's called Arthur Ashkin. Gerard Mourou was the second winner of the physics prize. And Donna Strickland is the Canadian who won the physics prize. Now, this is really interesting work because they have all worked on lasers and light and developed a process called optical tweezers. And what optical tweezers are, you can fire a laser beam and intersect it with another laser beam, and the interaction of the light paths means that you can create what we call an energy minimum and an energy maximum in a certain area. And you can imagine this as a bit like a landscape with hills and valleys. And if you put objects into this landscape, they roll naturally into the valley. So you can use light to create an energetic valley, and you can put objects in there and manipulate them. And people all over the world are now using this technique to move things, even living things like bacteria and viruses, even atoms, using this technique. And you might remember the iconic picture that was published of moving atoms of xenon to spell out IBM with xenon atoms about 30 years ago. Well, that was the guys who got the physics Nobel. The other development that Donna Strickland was involved in was the development of ultra-short pulses of laser light. And why this is important is if you just blast something with a laser, you're going to put a lot of energy and you might do damage. If you can make the pulses really, really short, the energy has time to dissipate, so you can do very precise sort of cutting and shaping of a surface. And we use this all the time for things like laser eye surgery. So that was the physics prize. Chemistry, actually one of the winners, this is Greg Winter, lives up the road from me in Cambridge. He's currently Master of Trinity College. I bumped into Greg Winter the other day, so there's my claim to fame. Frances Arnold is the American lady who's also involved in this, and George Smith is an American scientist who's the third winner of the chemistry prize. Now, all of this works or is related to protein engineering. Now, what Frances Arnold did, she was interested in trying to make enzymes that would work better. Enzymes are nature's catalysts. They're molecules which have the atoms arranged in just the right way that they will lock onto things and then help chemical reactions to happen in living systems. So inside your cells, the reason you're breaking down sugar and liberating energy from it that keeps you alive, that's all down to enzymes. We would like to use many of these enzymes industrially. But the problem is that the enzymes that nature endows us with are not necessarily the best at doing some of the jobs we want to do. And the insight that Frances Arnold had was to introduce genetic changes into the genes that code for these enzymes at random, and then select out the enzymes that do the job better than what she started with. And then you say, well, those ones are better. Let's change them a bit more and keep doing this until you evolve. You use the same process that nature has used over billions of years to make us what we are. You use the same process in a test tube to produce really, really good enzymes, but you do it in literally days to weeks. So that was one breakthrough. Greg Winter and George Smith, their insights were to do what's called phage display. The idea is you have tiny viruses that prey on bacteria normally. These are called bacteriophages, but they engineered the system so these phages, these viruses, can display on their surfaces proteins that are expressed from genes that you insert into the phage. Now, why this matters is that you can then use this to screen for genetic sequences that will make really, really good drugs. And the antibodies that we're now using in medicine have been evolved and developed using this insight. So that's an amazing thing. It's made enormous leaps forward in what we're able to do medically. The Medicinal Physiology Prize, James Allison, who's an American scientist, and Tasuku Honju, who's a Japanese scientist, they share the prize for breakthroughs in cancer therapy, what we call checkpoint inhibitors. When cells are dividing or when the immune system is interacting with cells, there are various mechanisms in place to stop cells growing or to stop cells being killed or staying alive when the immune system talks to them based on how healthy the cell is. They discovered a lot of these pathways, which if you fiddle with those pathways, you can make cancer cells kill themselves because cancer cells stop themselves using this pathway normally. So that's why cancers are a problem. If you disable this system that the cancer has evolved, you can start killing cancers again. So big insights and big breakthroughs in cancer therapies thanks to those two. So that's a quick snapshot of this year's roundup of Nobel Science Prizes.
Arthur, good morning. Welcome to the show.
Hi, good morning. I want to know, is our galaxy moving around, in other words, in a cylindrical circle.
Hello, Arthur. The answer is yes, it absolutely is. So our galaxy is a cluster of 100 billion or so stars, or maybe 200 billion, it may be even bigger than that. So a lot of stars. They orbit around a central giant or supermassive black hole, which is in the centre of our galaxy, and they take millions of years to make an enormous cosmic orbit. And of course, around each of the stars are planets like ours orbiting those stars. So the planets orbit the stars orbit the galaxy. And you can see that over millions of years, those stars do rotate around the galaxy. So if you were to go back millions of years ago and look at the night sky, you would see quite a different arrangement of stars in our galaxy than we do at the moment, because everything is moving relative to everything else. So yes, they do go around in a big circle.
Bandile, good morning.
Hi, good morning. My question is on biogenesis or abiogenesis, which is sort of the theories that explain how life arose from basically chemicals. So I'd just like to know the naked scientist's view on what the best theory is, how the Earth basically was a chemical, and then, hey, all of a sudden it's now a self-replicating cell.
Okay, interesting question about creation there.
Yeah, where did life come from? Well, the evidence we have is based on ancient remains going back up to 4 billion years. We've got rocks from, for example, Western Australia in the Jack Hills Formation, and you can see chemicals locked inside tiny rock samples, zeolites, and in those you can see the signature of, at least chemically, of life. So we think that life got started very early on Earth, certainly within the first 500 million years or so of the planet's existence. That life obviously would have been simple to start with and was almost certainly just a bunch of chemicals, because the Earth's surface would have been what people dub Darwin's little pool, where there would have been hot, wet, lots of ultraviolet radiation, because there wouldn't have been ozone layers and things to defend the Earth, so it would have been a pretty harsh environment, but ideal for chemical reactions to evolve. And what we think is probably the evolution or origin of life is nucleic acids, a bit similar to DNA or its chemical relative RNA. And these initial chemicals would have had a number of abilities. One of them is to store genetic information, because you have a sequence of letters and that sequence stores information. But the other thing these chemicals almost certainly could do is fold themselves up into interesting shapes, which would have given them the ability to be chemical catalysts as well. So we think, or the most favoured hypothesis at the moment, is what's called an RNA world hypothesis, which is that you have these early chemical reactions with primitive nucleic acid sequences made of chemicals like RNA, the relative of DNA. And this slowly specializes, in some way develops the ability to endow itself with a membrane, an oily bag around the outside, and at some point evolves to use DNA, not RNA, and that then gives us the first microorganisms that we would recognize as such. And then for about 3 billion years, not a lot happens. And then about 600 million years ago, suddenly you get much more complicated life, which is stemming off from this much more primitive early life. And the reason we think that's the story is that if you look at the genetic code, what sequence of genetic letters make instructions in one type of life, and you compare it with another type of life that has not had any kind of relationship with that type of life for hundreds of millions of years. So you compare, say, a jellyfish and a human. The same genetic code works in both of those organisms, and if you go back even further and look at a bacterial cell, even those use the same genetic code that's running in our cells. And this is why we think that life comes from a common stem that would have then diversified over millions of years to give all of the life on Earth from one very common, very, very early common ancestor.
Prasad, good morning. Welcome to the show.
Morning, Eusebius. Morning, Chris. My question is, I have had occasions to stay in cold places where there has been snow, and I've found that after a walk, my feet sweat to the extent that sometimes I can squeeze water out of my socks. Of late, I have started doing hot yoga, 41 degrees, where my whole body sweats, but my feet are dry. I'm quite perplexed. Can you throw some light on this?
Yeah, you're just weird. It sounds like you're, there's this
You're
saying.
from Cape Town, are you?
Well,
That's right.
Yeah.
I mean, there's this saying, you don't know your arse from your elbow. It looks like your feet don't know the one end of your body. They're doing the opposite. Yeah, I really don't know the answer to that, why your feet should be doing the opposite of what they should be doing. The reason we sweat is that you have in your skin sweat glands. These are aggregations of blood vessels. They're a little coil of blood vessels, and they squeeze the plasma, the watery component of blood, out through the wall of the blood vessel into a collecting system, a duct, which funnels the water onto the skin surface to make the sweat. That process happens under the influence of the nervous system, and specifically a part of the nervous system called the sympathetic nervous system, which activates what are called pseudomotor nerves, which promote sweating. And so in order to elicit sweating, you have to activate your pseudomotor system. It might be in you that some miswiring has gone on in your foot region, because it seems like the wrong thing is happening. When your feet are cold, you should be reducing heat loss. You should be restricting blood flow to your peripheries to conserve heat deep inside the body. And when you're too hot, you massively augment the blood flow to the skin surface, and especially to your peripheries, like your fingers and toes, because they have an enormous surface area to volume ratio. So they're really good at losing heat fast. And your body uses that effect to very great effect to keep your temperature right. So why your feet are doing the opposite of what they're supposed to be doing, I really don't know. But if it's working for you, it works for me.
Do you have a pair of left feet, Prasad?
I hope so.
Tali, good morning. Welcome to the show.
Hi, how are you?
We are good, thank you very much. Go ahead.
I'd just like to know concerning the Big Bang Theory. You know, it simply says that something exploded and became something. Nothing exploded, became something. So how do you reconcile that with the second law of thermodynamics? Or did the laws of physics not apply back there?
Yeah, tough question, because of course no one was around to see the Big Bang, and so everything we talk about this is conjecture based on the observations we can make. We know the age of the universe. We've got a reasonable estimate for that based on various missions and various measurements, including the Planck mission, which was a satellite mission a few years back. So we know that the universe is about 13.8 billion years old. So it popped into existence in the Big Bang then. We know that the universe started, or we're pretty sure the universe started as a point source, something which was infinitesimally very small, very, very rich in energy, and it suddenly pops into existence, and some process converts energy into matter. And this is E = mc squared. It's how energy and matter are interchangeable. And this energy is unleashed, and this energy gives rise to fundamental particles, and those fundamental particles then give rise to atoms. Once the universe cools, and because it's expanding and growing, it's cooling, and once it becomes sufficiently cool that matter can actually stay together, rather than being at such a high temperature it's ripped to pieces, you then get these particles coalescing to make material, matter. Most of what came out of the Big Bang was hydrogen. There was a bit of helium and a little bit of lithium. This then begins to coalesce to make stars, and those early stars, probably very, very big, very hot, very bright, lots of ultraviolet around, which would have had various effects. And it slowly spawns this aggregations of matter and material that we've got in the universe today. The universe is still growing, and as it ages, it grows faster. And we're still trying to work out why, as it ages, it blows up more and grows faster. That's down to something called dark energy, but we still don't know what this concept of dark energy is. But at the moment, we know that the universe is expanding, certainly following the laws of thermodynamics, because it's getting bigger and it's spreading out. Stars are burning off energy and spreading out their material more, and the matter in the universe is becoming more chaotic, more disorganized, and that means entropy is increasing. So in the future, if the universe keeps on growing the way it is, it'll be so big, it'll be expanding so fast that you look up in the night sky, there will be no stars to see, because the light coming to us from those stars will have been stretched out of existence.
702 and Cape Talk.
The Naked Scientist.
Anthony, good morning.
Morning. Hi, gents. Thanks for the great show. I've got quite a specific question. When restringing a guitar, the guitar string is secured between the bridge, if you're a right-handed player, on your right hand, and it goes along the length of the guitar neck and then over the nut, and then is tightened by the tuning peg. obviously you tune your guitar a few times in order to get it to pitch, but invariably on the other side of the tuning peg, there's a lot of excess string that is left flapping around and that type of thing, and is typically snipped off. So something that I've noticed is it's unused string. It's not contributing to the pitch of the guitar or the pitch of the strings or the instrument. However, when you snip off those unused bits of string, the tone or the pitch of the entire instrument is affected to the tune of about one semitone. I've always been confused by this. I wonder if you can talk me through it.
I can't. Maybe Chris can.
Do you know, I'm slightly confused by that, because you wouldn't expect them to play any role whatsoever in the note, as you say, for the simple reason that the way that string is working is that it's tethered between 2 points, and when you make a string vibrate, then those 2 points that it's tethered at, the end near your right hand and the end of where the neck is, where the tuning peg is, those aren't nodes where you haven't got the wave moving, and the string vibrates up and down either side of those nodes. So there shouldn't therefore be anything going on with those other bits downstream. The only thing I can think of is that when you trim them off, perhaps they are in some way applying just enough force onto the tuning peg to stop it moving. Because I know my daughter plays the violin, and if I'm not really careful, it's possible to just nudge them a little tiny bit, and because the strings are so taut, it's enough to knock it out of tune. And I wonder if the trimming action is what is just enough vibration to make the pegs roll back a little tiny bit. But that's purely my speculation, and I'm not a guitar expert. So if anyone can help us, I'd be grateful. But the physics is simple, that there shouldn't be any difference made to the note by those bits which are effectively not part of that vibrating string system. So I don't know, but I would speculate that perhaps it's just that we're untensioning the string, because I presume you're saying, are you, that the pitch drops a little bit once you've done the trimming?
Yes, it actually goes flat. So
yeah, so that would fit, wouldn't it? With
one at a time, yes.
It's energetically more favourable for the string to unwind than to tighten. So when you trim them off, I suspect probably it's knocking it back just a tiny bit. It's probably untensioning the string a tiny bit, and that is what is causing it. I think that's probably the reason.
Thanks, Anthony. Mish, good morning. Welcome to the show.
Hello. Oh, thank you, Sirius. I would like to know from the Naked Scientist, what does he make of the skeptics who doubt America's mission to the moon? Because we never had problems with Russia's Sputnik. Nobody had problems. After all, it was also a manned mission from America, not even not once, not twice. Many countless times, but there are skeptics who doubt, if America ever landed on the moon. Well, what does he think? Does he think that it's just politics, or what does he make of it?
Well,
we understand it was politics anyway, because the Cold War, Americans were forced to go to the moon as well.
I hear you, Mish. I hear you.
Yeah. Well, it's one of those things that it makes a good story, doesn't it? If you say to people, well, they made it all up, and then people are so surprised, and then you go, really? And then someone says, oh, yes, there's all this really strong evidence. They made it all up, and they went to all these extraordinary lengths to make everyone think they've been to the moon. Actually, there's no evidence they made it all up. There's lots of evidence they really did go there. And the evidence is that independently, spacecraft which have since orbited the moon or gone round the moon, including one called Smart 1, have actually taken pictures of the lunar landing sites, and you can see the materials that the astronauts put there on the moon's surface. So we're pretty comfortable that NASA did put its people on the moon, as you say, not once, not twice, not 3 times. They went there several times. And they've left those things behind, and we can see them. So we're pretty comfortable that'll happen. And people invent all these random stories about flags waving or not waving and all that kind of thing, and shadows falling in the wrong direction. It doesn't stand up to proper scrutiny. It just makes a good story, and people like telling it, but actually there's not really any evidence. It's just a bunch of conspiracy theorists. So we're pretty comfortable that we can believe NASA. They went there.
Coquette, so good morning.
Hi, Eusebius, and hi, Chris. Quick question. It's about the speed of light postulates. That objects traveling at the speed of light, changing length and mass. Has it ever been proven that an object that's traveling at the speed of light does change its mass, does change its length, and the calculation of classical mechanics no longer apply? Has there been experiments that have proven that?
Thanks, Oketo. That sounds very clever. I have no idea what it means.
Yeah, well, what he's referring to is the equation E, energy, equals mc squared, mass times the speed of light squared. So in other words, energy and mass are interchangeable. And if you give something more energy, and when you speed something up, it has more kinetic energy. So if the E goes up, then to keep the equation balanced, because c squared, the speed of light, isn't going to change, the mass must increase. So as you accelerate an object, the more energy you give it, the heavier it becomes. Now, that's the best argument I've ever heard not to take exercise at school, because that's like saying, well, if I go for a run, I'm going to get heavier. So this is a bad idea. Exercise is not good for you. Unfortunately, when you slow down again, the effect reverses. But transiently, while you're running, you will have more mass. You will have got heavier. But the bottom line is that as you accelerate something towards the speed of light, the mass increases. And as you increase the mass, you're going to need to give it even more energy to accelerate it more. So therefore, both the energy and the mass tend towards infinity as you get towards the speed of light. So that's why we think it's impossible to accelerate something, apart from light, which is massless, beyond or to the speed of light. Things will get very, very close, but they won't ever get there. The protons at the Large Hadron Collider are going within a few meters a second of the speed of light, but they're not going to the speed of light because we're having to give them so much energy to push them along. You can't make them go any faster. So I'd say that the LHC, the particle accelerator at CERN, is a really good example of E equals mc squared being demonstrated for us.
I feel so much guilt because this last gentleman has been holding on for a very long time. Let's squeeze it in very quickly. Bram, what is your question?
Good morning. Hello. Another weirdo from Cape Town, UCBS. I was walking on the beach the other day and the foam was so heavy that you couldn't even see the water. And then I thought, where does this foam come from? Who throws the...
Excellent question. Where does foam come from in the ocean, Chris?
That foam is caused by proteins and other things which reduce the surface tension of water. They have a detergent-like effect. There are proteins made by plants. There are other small molecules which are made by the animals that live in the sea, and they have the effect of getting between water molecules and reducing the bonding, the hydrogen attractions between the molecules. And if you weaken that attraction, the water can form a thin film like a bubble. And that's exactly how detergent and soap bubbles work, but the sea just naturally is making, from the things that are in it, the organic matter and the plants and animals and so on, it's making its own detergents which have this ability to reduce the surface tension and make that foam. And when the wind is right and the currents are right and the sea is choppy and it all mixes all these things up and introduces air into the water, as you get water splashes above the water surface, you will have a chance to make a thin bubble. And so you get this foam, especially on a windy, choppy day. And that's probably what Brian saw.
Thanks, Chris. We'll do it again next week.
I'm looking forward to it already. Thanks, Eusebius. Bye, everybody.